What's up, guys? We're back with another CCT episode. Let's jump right into a random easy problem. This one I have not attempted. I just briefly looked at it a minute ago, and we're gonna see if I can do it first try. All right, so listen to how I struggle with this, and get my thoughts down. I'm also gonna put on this little glove that's meant to make this board a little easier to use. I mean, it's a really nice board. I highly recommend it. It's the X Pen is what it's called. It's really fancy, although it's not that expensive. It was only 60 bucks, and I got it kind of as a, well, I wouldn't say Christmas, but Hanukkah, Christmas, New Year's, that kind of present. And it's really nice. Okay, so let's see. So this is saying we have to return true or false if this is a balanced tree. I don't know if you guys know what. So, okay, a balanced tree is. Let's make a new thing here. New. No. Okay, so a balanced tree is when the height of a. The height. Sorry, the height from a certain point is the height on the left side and right side of a node is within 2 or less than 1. So for example, the height here is on the left side would be 2, and the height here would be 1. And so that's okay because the difference between the height here and the height here is 1, so that's fine. If, however, we had this, then it would not be fine because the height here would be 3 and the height here would be 2. Okay. And then it would also, so not only do we have to check that, but we also have to check from every single node, like to make sure the height is good here. And it is, like, you might not think, how is it possible that the height is good here and not good here? Well, let me show you. So let's just say we have something like that, and then 1, 2. So then the height on the left side is going to be 1, 2, 3, 4. Height on the right side is 1, 2, 3. Difference is less than 2 because it's 1. And so that's good. It's good from this node. Then we have to check from this node. Is it good? No, because we have a height of 1 here and a height of 3 over here. Okay? So this is also the basic concept for AVL trees. AVL trees are a way of turning basically a vector into a binary tree such that it is relatively evenly distributed so that you could do like binary tree search, because it's possible to end up with a binary tree like this if you are adding in things from a vector that are sorted, for example, which is common. And so something you want to do is like this is a bad tree to work with. Like there's literally no benefits to having a tree that's like this. You have to like rotate that and then rotate it here. That's a whole AVL trees are a whole different beast, but that's the basic concept. You want the how do they say it? You want it to be balanced, basically. They call it the depth of two subtrees if there's no more than. Okay. Yeah, I guess that is depth, not height. Wait, the depth is. Okay. Actually, let me just look up the difference between depth and height because I always forget it. Height and depth. GG. Geeks for geeks. It didn't come up, no. I don't know. Let's just look here. I mean, come on. There's got to be a better. Here's your number of nodes, height. Nope. Okay. Still no. So it's saying the depth of the tree is no more than the depth of the other subtree. Right. Oh, okay. I remember what depth is. Depth is like from the bottom. So the depth of here would be 3. The height of here would be 1. Depth is how many from the bottom, like the longest way to the bottom, and height is your way to the top. There's only one way to the top. Okay, so that's the difference. So actually, I should say the depth. Okay, so I would like to make a helper function called int depth. And it takes in a tree node pointer root. I'll call that root also. And so I want to return I kind of want to be like recursively calling this. I want to call it like at every node basically. Well, I could just do some kind of like breadth first search or something. So like queue of tree node pointers queue dot push root while queue is not empty. Basically, I'm gonna say return. So if depth at okay, there we go. So queue dot auto temp gets queue dot front queue dot pop. I feel like there's a more efficient way to do this, but I'll just do it this way. So depth at temp. Sorry, I like doing left first. I think I could do abs, so the absolute value between temp left and minus the depth of temp right is less than 2. Sorry. If it's greater than 1, actually, return false. Yeah, and it can take in null node, so it's okay if that's fine. So if temp left is not null, then q dot push temp left. And same thing for if temp right is all cool, then q dot push temp right. Okay, so then if we get through all of that, then just return true. Okay, now to here. The depth, to compute the depth, I'm going to do this recursively. This is pretty much the same as height, how I computed height, which is why I was confused between height and depth. So if root is empty, return 0, else return the maximum of depth root. I'm doing so many subproblems, which makes me think like there's a faster way to do this. And depth root right plus 1. Yeah. So that finds the max of that, hopefully. You want the max because it's like, if we're here, what it's doing is it's calculating 1 plus, it goes through here, sees that there's like 0 and 0 or whatever, so then it's going to do 0, so it's going to be 2 from this side, it's going to, or sorry, it's going to be 1 from this side, and this side is going to be 2, so then it's going to be 2 is greater than 1, and then return 3. Right, because the plus 1 is for your current node, and then you go left and right and find those depths. This is a classic thing. This is also the same for to find the tree height, which yeah. Okay, anyway, so then, well, now I'm confused about what depth and height are again. Height versus depth tree. What is the difference? Can I just see a picture, please? Okay, whatever. So let's see, if it's empty, I just want it to return true. If not root, you could just return true. Okay, I think this is correct. It might take too long though. This is a really bad time complexity, I think. Oh, wow. That is impressive. I was not expecting it to be the fastest solution. Well, that's pretty nice. So it did like the idea. So basically here I'm doing just a recap of breadth first search. Always got to remember this edge case with there's nothing in the tree. Then while it's not empty, we first make sure that current node is has a good difference in heights or depths, whatever, and then we go to the left and make sure that's true, and or no, sorry, we push the left side in and the right side in if they're not null, and then we make sure the same thing is true for those two. Okay, well, okay, I will get back to you in my next video what the difference between height and depth is, but I think they're just basically the inverses of each other. Like height might be from the bottom and depth might be from the top, but I think it's the other way around. Okay, anyway, thanks for watching. I hope you enjoyed the video. I'm kind of surprised I got this on my first attempt. I usually don't get things on my first attempt or have to come back like after and re-record the video. Cause like I don't want to give you guys something when like I can't figure it out at all, you know? I mean that's kind of a waste of your time. Not that. Okay, never mind. But um, yeah, I hope you enjoyed this video. So this is JC signing off. See ya.